All right, the goal of today is to finish the last conversations on this list, okay, as well as just work some general problems with you so that you can see kind of, all right, Spainhour, great, you did this whole spiel or whatever. How can we use this? All right. I believe we ended at acceleration equals vt over r. Okay, let's say this real quick. You're going around a turn in your group. You're going around a turn. You want to minimize the amount of acceleration necessary. Okay, what do you do? Let's discuss in your group real quick. Gabe, you're on that. You pull. Okay. Let's say that differently. Okay, well, okay, you tell me what the answer is because it's quick and too fast. I realize after I ask the question, it's kind of a dumb question because it's just rote memorization. What are the things that you do? Slow down, okay? And if you had the option of an open field, obviously if you're getting off, say, the interstate or whatever, what can you not control? Sure, therefore, in that equation, what can you not control? Your radius, right? You can't control what size of your radius on this particular thing. I guess if you could, but if you go too small, you're leaving the thing, right? And if you go too wide, you're leaving the thing. So anyway, you see that hopefully, okay, I realize I'm potentially getting ahead. Whenever I draw any curve, okay, there is a radius to that particular curve, even if it does not complete a circle. Yes? You've seen that, right? This would be a, and sometimes the center of that circle is not actually in the turn itself, but hopefully you can see, yeah, radius 1, smaller than radius 2, smaller than radius 3. Okay, moving on. So yeah, slow down. So new question then. In terms of this standard definition of acceleration, why is it that slowing down will cause a lower acceleration? There are two things you need to address. Discuss that in your group. Why is it, in terms of that equation, that slowing down will cause a lower acceleration? This is a conversation almost verbatim that we had yesterday. All right, what you got? That's the first one, correct. Slowing down will increase the amount of time, therefore your change in velocity can happen over a larger period of time, therefore lower acceleration. But what else? This one I tried to share with you pictorially yesterday, and it's basically this. If I go from here to here, that's roughly a 45-degree turn, right? As you said a second ago, to get from there to there is going to take more time if we slow down. Cool. But the other thing to consider is this. If I draw it in the first case, right, where I have kind of a high velocity, I'm going to draw it straight up, just like this one. I'm going to draw this one roughly at, I said 45 degrees. Notice that I drew both of those arrows in an attempt to be about the same size. Okay, this is velocity initial, this is velocity final, that is the change in velocity. If I then severely lower the speed, notice I attempted as best as possible to do the exact same angle, okay? But notice what happens to the change in velocity vector. What happened to it? Yeah, I don't have to change as much velocity because my velocity is not as, because it's not as big. Does that make sense? So it's kind of in a way, in a very simple way. If I said, hey, you're going 10 meters per second, and then you're going, say, 30 meters a second, which one is going to require a greater change to get to zero? Okay, obviously it's going to be the 30. It's going to have to change a lot more. Okay, this one is saying, hey, you have 30 meters per second, you have 10 meters per second on the right. Which one has to change more in the same angle? Well, the one that's going faster has to change more, okay? Or vice versa, the one that's going slower has to change less. So the answer I was looking for there, two answers, are number one, as we already said, can take more time. And number two, at a smaller speed, you're actually changing less velocity. And we see this reflected in the fact that that guy right there is squared. Meaning, if I actually cut my speed in half, how much do I affect the amount of acceleration? If I cut my speed in half, how will that affect acceleration? 1/4, correct. Which, if you don't struggle with that, just plug essentially a 1/2 in here, square it to get 1/4, assuming that the r stays exactly the same in both cases. All right, let's get on to the inertia conversation. We did this whole thing yesterday where, and I think we did it on day 1 too, where I talked about the fact that when do you get a centripetal acceleration? When acceleration does what? Perpendicular, right. You start at perpendicular. And then I said, all right, let's run through this list. If it's perpendicular, it will change direction. If it changes direction consistently, because it's consistently perpendicular, if something were to consistently change direction, what shape would it make? Well, it would make a circle. So if it makes that circle, because it stays perpendicular, we can also say that acceleration points towards the center of that circle, and thus the meaning centripetal. Centripetal towards the center. Does anybody know what the counter of centripetal is? Centrifugal, correct. You see this in a centrifuge, and people sometimes goofingly talk about centrifugal force. Now, why do they talk about centrifugal force? Well, imagine, if you will, that you are in a car. Okay, or actually, let's put you in a bus. You're all in a bus. Okay, no seatbelts and all that. Here you are in the bus. Person, we are on the top-down view. Here's the driver. Okay, going this particular way, and the driver doesn't care about themselves or the road or anything, and is going way too fast for a turn, goes around a turn, okay? What do you expect to happen to you in that seat, especially if you didn't see this coming? Right. You actually go the opposite way of the center and the radius. It feels like there is a force pressing you to the outside, okay? There is not a force pressing you to the outside. Why would you go to the outside part of the circle if this is the case? Well, let's think about what you naturally want to do, okay? Here you are, you're driving, okay, you're passenger, okay? You have a velocity this direction. What is the natural state of that velocity? It wants to keep going that way. Right. The bus turns because the bus has a series of forces on it. Are those the same forces on you? No. So what do you naturally do while the bus is turning? You keep going straight. The reason you get, quote unquote, thrown to the outside part is because you are attempting to go in a straight line path, and arguably the bus is sort of jumping out in front of you. It's jumping out in front of your way, which is why you run into the particular side. This is also why, if we view like a top-down view of like a washer and dryer, I'm gonna draw some clothes here, nailed it. Just, I mean, you don't have to question my artistic skill. There it is. Where do you find clothes at the end of a spin cycle? All pressed on the outside. Why? Why in a circle is everything pressed on the outside? Well, because naturally an object wants to go straight. So if it wants to go straight, that's where it's going to go. The problem is, of course, the wall gets in the way. So when we talk about centripetal acceleration, okay, what you have to think about is basically this is the necessary force and acceleration to keep it in a circle. Do any objects want to stay going in a circle? No. We talked yesterday about the fact that static friction is the one that's used by people and cars, right? Because it points the opposite of the way that you want to go. So here you are in a car, like we said yesterday, you kind of naturally want to go towards the outside radially because you're trying to go straight. So instead, static friction goes in, right? Where's friction? Static goes towards the center. But do you remember how there's actually a maximum static friction? There's a maximum static friction. Underneath that maximum, it's 1-to-1. However much it needs is exactly how it's going to apply. But if we go beyond this point right here, if I go and I require too much acceleration, here, let's just do it here. Okay, so here's the force friction. So I'll just do this guy right here. Force friction is causing this acceleration. If I need too much friction because I require too much acceleration, then I'm going to break this spot right here. I'm going too fast. And what would happen to your friction if you have too much static friction? Become kinetic. And does kinetic point towards the center? No. Which way does kinetic going to point? Opposite of motion. And this is when you do what if you're going too fast around a turn? This is when you would slide. This is why you slide if you go too fast around a turn. You actually saw it yesterday with me spinning the wheel and the thing falling off. I spun it too fast. It was greater than static friction. There we go. So inertia is what keeps things going towards the outside part of the circle. It's why you feel thrown to the outside when you're actually not thrown to the outside. If this bus is going normally, by the way, if this bus is going at a normal speed, not like crazy fast, what force is it probably on the person that keeps them in a circle? If you're sitting, just imagine you're sitting in a seat here. Here you are on a bus. Okay? And the bus is out there. They go at a normal pace this way, so I don't have to be like crazy or anything. What force is it that takes you in a circle, probably? Static friction of your butt. Okay? Now, what happens if you require more than that static friction? Well, A, you should see yourself slide because it's not enough, but when you will definitely keep going in a circle. Okay? When will you stop sliding? What force would be applied to you that will make sure that you keep going in that circle? What will happen to me? So here I am. Okay, here it is. Just use all your imagination here. We got the aisle over here. I'm sitting by myself. Okay. No shot there. All right. Anyway, okay, and I'm sitting by myself. The thing goes really fast, and I go, whoa! What happens that then forces me to actually stop going to the outside? What's that? Yeah, the window, the wall. So what force is there? Normal. Right. Normal would then be what keeps you actually in that particular circle. All right. How are we doing? Now, here is an important note on this particular subject. Let's come back to this guy real quick. Speed and radius do not cause acceleration. They do not cause acceleration. What they do is they ask how much acceleration is necessary. What is the cause of all acceleration? Unbalanced forces. So, what I would do if I were you is I would pretty much always start right here. Unless it's just talking about acceleration, you're more than welcome to start up there. Okay? I would start at this spot pretty much every single time. And then, what you do typically in physics is you go, all right, let me do a force diagram, right? And you do your force diagram and you figure out that, hey, my velocity is this way and my forces are that way. Which means what's the direction of acceleration? Also that way, right, to the right. And the fact that it's perpendicular makes that centripetal. And in that moment, what I usually do is just substitute into this equation. That right there over there, okay? What this does is it says, hey, because of this speed, because of this radius, this is how much acceleration I require. Last thing on this subject I'm going to say is this. If we just talk about linear acceleration, what's the maximum that probably most people would experience? Like what's the force, what's the most acceleration that most people get probably on a day-to-day basis? Gravity, 9.8 meters per second squared. And people are used to that. You know how they're used to it? Because if you just take this simple force diagram, obviously you normally experience how much force it is to get your gravity, to get your Wait, are all of us in here at the same force of gravity? No. But what we can do is we all know what one gravity feels like, because that's exactly what we feel every single day. That's how much force it's necessary to get that. So what a lot of times we do in this is acceleration centripetal limited by that same amount? Is acceleration centripetal limited by 9.8 the same way that linear is? No. This right here is the primary acceleration that most people feel on roller coasters. If you ever hear that a roller coaster gets past 4 Gs or 5 Gs, that's actually just talking about centripetal acceleration. The reason they use Gs is simple. It's very simple. You know what 1 G feels like. So if I say 2 Gs, how much force is necessary for you to pull 2 Gs? Twice your weight. Okay? If I say, hey, we need you to pull 6 Gs, it's literally just saying, hey, the acceleration is 6 times 9.8. For humor means sake, about 60 meters per second squared. That is 6 Gs. Okay? A G is not a new thing. It's just a fraction of that particular acceleration. Let me tell you a real quick story on this, and then we'll move on. When I was young, I played a fantastic game by the name of Roller Coaster Tycoon 2, I believe. Okay, and in this game, okay, you design these crazy roller coasters, and they would give you a score at the very end. Now, I, not having the physics background at the time, thought, here's what you do to make the best roller coaster. You make it as tall as possible. Okay, as tall as you possibly can. So they're going fast. Okay, they're going real fast. Right? And then they get to the bottom. What you do is you spin it as fast as you possibly can, just in a circle, okay, as much as you possibly can. All right? And I would get done, and they would give you like 3 scores. There would be like enjoyment, nausea, and intensity, I think. And I would always get the following scores: super high on nausea, super high on intensity, and super low on enjoyment. And I couldn't figure it out. Now, I also had this other thing that they did, which was really cool. They had this chart that actually measured the Gs that people were hitting on this ride. And they would tell you the maximum. And I didn't know what a G was at the time, but now you do. Okay? And so I was spiking out a maximum of 12 Gs. My riders were experiencing 12 Gs. So what I'd like you to do right now is humor me. Okay? Take your weight, plug it in the calculator, or anything close, make it up if you want, and multiply by 12. Okay? Multiply that by 12, and that's what you would have experienced, okay, on, now, I think it's also an important fact to look up, okay? You have a number sitting in front of you. I'm just going to compare it so you have some kind of frame of reference, because you don't probably experience those type of forces regularly. Okay, let's look up force necessary to break a spine. All right. About 3,000 newtons. So 3,000 newtons divided by 4.45. About 674 pounds is what's necessary to break a spine when put in the right direction. Okay, that's got to be a little bit off because there's some other things at play there. I know you could experience more force than that, but what was, anybody volunteer, what was your force that you would experience at 12 Gs? 1,356. And if that doesn't have good frame of reference, if you have ever gone to the gym, okay, if you've ever gone to the gym, those bars that are up there are typically about 45 pounds. Typically, you put plates, so one plate on either side puts you at 135. Okay, so a 135-pound person has to have 12 of those bars stacked on top of them to get 12 Gs. This is where you get a primary amount of the acceleration on a roller coaster. When somebody spins that way, okay, this tells us how much acceleration is necessary to pull that particular thing off. Yeah, all right. So let me finish this last conversation, and then we'll do a problem along those lines. The last conversation we have, and I'm specifically bringing it up over here because I know you asked this question a little bit yesterday, Lillian, and I want to make sure I actually do legitimately. I actually got another one. And I lost that one too. How did I lose 2 of them out now?
Did you ever get to roller coaster Tycoon 3?
I've gotten to a lot of them.
Do you have like the skateboarding one, like Skateboard Tycoon?
Sure. I don't think I've done all the tycoons, but I definitely played the crap out of the second one.
So
all right. I imagine it is. All right, both accelerations. So what is acceleration centripetal again? Acceleration perpendicular to velocity is acceleration centripetal. Okay, I'm going to give some names to some other ones, okay, that we have technically already used, but we're going to get a little bit more specific. Just standard acceleration that we've always used is the exact same thing. It's the change in velocity over change in time. But right over here, I'm going to put this once again. I know I put it up here a few times. Velocity is speed plus direction. So the next thing I'm going to share with you, which is slightly different, is acceleration tangential. Okay? Now the great news about acceleration tangential is this is not a new acceleration, even more so than centripetal. This is what you have used a bunch. If acceleration centripetal is when it's perpendicular to velocity, guess what tangential is? Parallel. Yeah. Now you already know what that does. If I have a velocity to the right and an acceleration to the right, what does that do? Yeah, essentially, in a nutshell, acceleration centripetal affects this one, acceleration tangential affects this one, and acceleration here says, yeah, but technically it could happen to both. Okay, so we have looked at essentially this. We got a velocity here, okay, and running it through again. That is acceleration, but we would call that acceleration tangential because it's parallel, okay? Usually we don't make a distinction early on because we just want you to focus on acceleration. Then, this is, yes, it's the acceleration, but since the acceleration is perpendicular, we can also call it centripetal. So where you really see these push is when you get a situation, let's imagine a car has a top-down view and acceleration is going this way. What's going to happen to that car? Well, the good news is what we can do is we can just do basic components. I can say, hey, this is the component perpendicular and this is the component parallel. This component that is perpendicular is called centripetal, and this one's called, come on. What are you, come on, kid. Tangential. And so what you do is you look at that situation in order to know what's going on, and you would simply say, if we imagine this as a top-down view, we would say, oh, the centripetal this way means the car is going to turn right, okay? And the acceleration back parallel, but the opposite way, means this size of the arrow or the speed is going to slow down. So if I gave you, the only thing you'd have to be doing on this is I would say something like, hey, here's your velocity, here's your acceleration, tell me what the car does. Here, someone humor me real quick. What's the car do? It's going to turn left and speed up. Correct. Now, mathematically, I don't think we're ever going to mess with too much of this right here. We might deal with a little bit. I'll point out some particular spots where it potentially could happen, but you're not going to be asked to calculate anything directly like this. You're usually going to be asked to direct acceleration centripetal when we are perfectly in this particular situation right here. I don't fully remember your question yesterday. I do remember it belonged to this conversation.
About like, do you know that if it's perpendicular to the velocity, like always if it's gonna like be like a cue for acceleration centripetal?
Sure. Okay, so I think this does then definitely speak to that. If it's perfectly perpendicular and it stays perfectly perpendicular, then it's going to be centripetal, right? Your situation's like, I think, you know, this guy right here. Why does it stay? Why does it, ow, does it stay perpendicular? Well, because it's literally just connected to this object, right? The object is moving tangent, and so you can see that the string is naturally kept at 90 degrees. My clothes, in the dryer example I talked about earlier, the clothes are going to attempt to head, oops, wrong thing there. My clothes are going to attempt to head this way, so what's keeping them from headed that way? Of course, they will head that way as long as they possibly can. But when will they stop? When they hit the wall. And if they hit the wall, the wall is going to push them perpendicular because which way does force normal push? Perpendicular to its relative surface. Yes? Why does gravity point perpendicular for that? You get the idea. Okay? These situations occur where it stays perpendicular, and so it stays at centripetal acceleration. All right. How are we feeling? I'm done with the conceptual stuff. It took me a hot minute. Yes?
Do we need to be concerned about gravity, like affecting acceleration centripetal, or is that only whenever like it's so
Yes,
small?
and we're actually going to see that example here in just a sec. There was a situation, there was a problem that I shared with you back in Forces, and I told you something was the case that I told you it's going to be weird right now, don't worry about it, and it was this. There was a person on a swing, okay? There was essentially a person, I think it was like a Tarzan situation, it might have been on the quiz actually, okay? And I said, what's the force diagram, okay? And the force diagram here, just simple stuff, force gravity down, force tension up, blah, 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 okay? Now, the time that I was, now keep in mind, in this situation, kind of Tarzan is going to go in this like half circle, which means the direction of velocity is changing. Yes? So humor me real quick. What is the force diagram of Tarzan at the bottom of the swing? Don't worry about air friction right now. Go ahead and do that real quick. What should the force diagram be of Tarzan at the bottom of the swing? All right. Two forces, that's it. What forces should be acting there? Force gravity. Now, here's the true question. I don't think you had any issue with that whatsoever. Should tension be greater, equal, or less than that of gravity? Greater. Why? Sure, but like if he was, for example, if he had just been hanging on it rather than actually traveling in a circle, what which one would be greater, or would it be equal? If he's just hanging there, right? There's just a string, right? And he's just hanging on a rope. The force diagram is obviously force gravity and tension. Should tension be greater, equal, less? Equal. So the question that I have here is, why is, you're 100% right, I don't want to take that away from you, why is force tension greater here? Okay. The acceleration has to point up. Why does acceleration have to point up here? Let me help a little bit. Pointing towards the center of the circle. Or, another way to put that, that's 100% right. The other way to put that is, which way is he changing direction? Upward. So which direction does the acceleration have to be? Upward. Okay? So, we're going to use this, and I'm going to give you some numbers here to calculate, all right, what is the force tension in this particular case? Okay, let's say the mass, let's make something easy. Tarzan's going to be a big old boy, 100 kilograms. The speed that he's traveling is going to be 8 meters a second. Keep in mind, by the way, sometimes radius is going to be listed differently. Like in this case, I'm going to say, hey, the length of the vine is 3 meters. When I say the length of the vine, always draw the picture, please. When you draw the picture, there's two things you want to consider, and sometimes you want to draw two pictures. Okay? The things you want to consider when drawing the picture are, one, you should be able to see the circle, okay, that he's going to, and two, you also want to be able to see where a good direct depiction of the forces. In this case, I think both of them kind of overlay the same type of deal. So there we go. So let's say the radius is 3 meters. The question is, in this particular case, how much is force tension? Now the good news here is that this next thing, all the work I'm about to show, I'm going to go pretty quick because it's all review. What do I mean it's all review? Well, looky here. You have your force diagram. Yes, this is just going back to chapter 4. So how am I going to start? I am going to sum the forces in the Y. Now, you have two possible options here on what to do. I don't care either way. Some people like both for different reasons, okay? The first thing that you can do is something that I pointed out a second ago. Since the velocity, which way should the velocity of Tarzan be at the very bottom? To the right, okay? There you go, there's the velocity of Tarzan. And what's the direction of acceleration? Said it's up towards the center of the circle, or upwards because it's changing upwards. Since it's perpendicular, we know that this acceleration is centripetal. And since it's centripetal, you can then take this, I would always start here, but you could take that and then substitute right away. The other option that you can have that some people really like, and I understand this, is actually just to go calculate acceleration centripetal separately over here. The value in doing this is it gives you a really good perspective on how much acceleration this is. Like in this particular case, this acceleration is ridiculous based on what we said earlier. 8 squared is 64, divided by 3 is 20 some. So this apparently Tarzan's experiencing 20 G's. I just made this number up on the spot, so it kind of makes sense. But anyway, so that allows you to calculate kind of separately. What should the units be of acceleration, by the way? Meters per second squared. It shouldn't change. I don't think I did this the other day, but just to show you that, this is meters squared over second squared, because that's squared, over meters. And yeah, it cancels out correctly. It still is meters per second squared. Humor me, what is acceleration centripetal in this case?
2,133.
All right, I got to change this a little bit. He's not. I can't. Like, I was just gonna let the ridiculousness stand, but that's 200 G's. That's like literally no. All right, 3 meters would be reasonable. I mean, I guess it's kind of long. 8 meters per second is kind of fast. Let's go to. I mean, this is still bad, but let's go to 5. What is that? 25 divided by, so it's still 8. No, that's not bad though. 8 meters per second. So like you're almost at a G.
We should have kept the 200 G.
Yeah, that'd be ridiculous. What is it? It's 8.33, right?
833, but I
No.
I think I did that wrong.
Yeah.
8.3.
Yeah. Okay.
I plugged it wrong.
So your other one was probably 2,000. It was probably 20, but still pretty big. Okay. Now, you can either do it over there or you can do it this way. I'm representing both over here. You do not have to do both. But watch here. Instead of sum of forces, since we are trying to find force tension, this is very similar to those impulse momentum problems and very similar to the problems we did back in chapter 4. And all you do is, how do I get the sum of forces in the y individually? You just do that same old thing. Is it in the y? Is it positive? Is it only in the y? Right? In this case, we would say positive force tension minus force gravity. And there we go. Now, here's a question for it. Well, actually, I'll finish the problem. We're trying to find force tension, so I'm going to add force gravity. Actually, while I'm adding force gravity, what's force gravity equal to? What equation is force gravity equal to? mg. Forget that g is not negative. We have already taken care of the negative here. So while I add it to the other side, I'm also going to turn it into that. All right. Does m cancel? You could factor it out, I suppose, if you wanted to. You also don't have to. But no, it doesn't cancel because ft does not have an m. Also, if you had done this over here, you don't need to have this as vt squared over r. You need to have this as an important conversation. This is a. And the reason we need to have this conversation is there a difference between a and g in this case? Yeah, very much so. A is how much acceleration centripetal you're experiencing. G is how much acceleration gravity would cause if it was by itself. If you look at my picture quickly, here's the gist, okay? How big does force tension have to be? Well, it at least has to be as big as force of gravity, right? Then it needs extra in order to provide that acceleration. In terms of the equation, here is the extra, here is the force of gravity that we're talking about. Make sense? All right. So this should be, I'll do it both ways again, even though you don't have to. 80 kilograms times 8.33 meters per second squared plus 80 kilograms times g. It's going to give us an answer. We did. I don't know why I switched it to 80 randomly. My apologies. I did that so numbers would be simple, and then I made them not simple. My apologies, yeah. The other way that this could have been done, of course, if you had not calculated that individually, would have been 100 kilograms times 5 meters per second squared over 3 meters. But of course, this is this. That's why they're the same thing. And both of those should give us what? 988 something. It should be 17 something? 1,007? 1,800? What are we at? 1813? Let's go 1810. Does it make sense? Oh, by the way, let's well, we can do this in our head. What was the weight of Tarzan? The weight of Tarzan is 980. Does it make sense that the tension of the rope has to pull that much more than Tarzan's weight? Yeah, because it has to be bigger. It has to be larger in that particular direction. How are we feeling? Now, there is one thing that is a little bit different relative to chapter 4, and it wasn't different here because of what you'll see in just a second, and that is how we define positive and negative. Typically, we're very used to this being our positives, right? Up and left, up and right are going to regularly be our positives standard. In circular motion, positive is defined as towards the center of the circle. Okay? Now, in this particular case, we're good because towards the center of the circle is up, and so that is positive. In this next example I'm going to give you, though, that's not quite the case. Here we go. So here's my next example. You ever been driving over a hill in the country a little bit too fast and it feels like your heart rises or your stomach kind of rises off of its normal spot? That's because it does. 100% it does. As a matter of fact, if you go fast enough over this particular hill, you can actually be in free fall, or arguably orbit. But we'll talk about gravity more tomorrow. All right. So let's just pretend that you're going over this hill. Okay? Now, obviously, force gravity goes down. Right? So watch this. I've kind of drawn it way more curved than it would actually be to emphasize my point. But is the car going in a circle? Yes, or changing direction. In what direction is it changing direction? Up, down, left, right. When the velocity is, sorry, let me start with this. Which way is the velocity at the top of the hill? To the right. Okay? Yeah. To the right. And in what direction will that velocity now change? Down. Or you can kind of think of it like this. All right? So what's the direction of centripetal acceleration? Which means it's also down. So what does which direction do the unbalanced forces have to be? I know I'm hitting the nail on the head here, I'm sorry, but it's kind of helpful, I promise. Down. All right, new question. Finish that force diagram. Think about everything I just told you. Okay? Finish the force diagram as you're going over the hill. Don't worry about the force of the engine right now or friction. We'll assume those are just balancing each other out. All right, what other force should go up here? Force normal. The tricky question. Should force normal be greater, equal, or less than force of gravity? Weirdly less. And this brings me to this particular point. You actually don't feel your weight at all. Your body does not feel weight. And you know this because when do you arguably feel weightless? Free fall. Do you not have weight in that case? do. As a matter of fact, if you're on Earth, does your weight really change, assuming you're not eating like a cheeseburger? No, it doesn't. But it does feel like you have different weight from time to time, yes? What you are actually experiencing, what your body uses to tell its feeling of weight, is force normal, the push against it. Don't believe me? Try this with like a yo-yo or something, okay? Try this. This will feel correctly like its weight, but think about what its force diagram is. Right now it's force gravity down, force normal up, obviously they're equal. Now if I yank on this though, okay, or if I let it go to the bottom where it needs to accelerate, does it feel like the same weight? No, it feels heavier. Not because it actually is heavier, but because what did force tension have to do to cause an acceleration up? It had to increase. When you go over the hill here, okay, do you feel the same weight when you're going over the hill? Because why? Force normal decreases. Force normal's not pushing as hard because you don't need that much, you need more acceleration downwards. So, the question is, how fast do you want to go over the hill?
20 meters per second.
No, let's book it. You're going 45. What are you traveling? I mean, I bet you travel a Humber at the normal speed, don't you? I bet you get past like it going 80 on Humber, don't you? Okay.
Down Humber, like the country roads, I guess.
Sure. I'm giving you a hard time. But like, let's talk about people that are probably not doing what they're supposed to. How fast are they going? 70, 80? Yeah. Okay. 80 miles an hour. Now it's kind of hard to see this, but the radius of one of those roads is obviously very big, but there is a radius to it. I'm going to say 200 meters. Mass of the car, let's keep it easy. Let's say it's roughly a ton, 1,000 kilograms. Apparently you're in your Honda Accord, or a Civic, or I don't know, something like that. You're not in a truck or an SUV. It's like double or triple that. All right. Now the question is, how much is force normal in this particular case? And it's a very similar problem. I'm going to do the conversion of 80 miles an hour for you. Just what are we usually using here? 2.25, something like that, 2.24. So this should be 35.6 meters a second. And see if you can't set up that problem entirely without me. I'll do it here in a couple minutes. Keeping in mind, what direction should be positive? Down. So when you do your sum of forces, this is where it's going to come out. That's going to be positive, and force normal is actually going to be negative because it is not towards the center. Which one do you want me to do? Do you want me to plug the equation in? Do you find that easier? Or do you find calculating it to the side easier? What's that? Plug it in. Okay. So I'm going to go, this is going to be force of gravity minus force normal equals mvt over r.
Do you usually use like acceleration centripetal in like another part of the problem?
Sometimes.
Okay.
Sometimes. I show you both because quite frankly, I'm going to guess that you're going to use both. I'm going to say that you want to be able to do both, not just kind of, be able to kind of see what's going on under the hood while you're doing this. But sometimes what I like to do to give myself context is I will do it exactly like this because it's a little bit more efficient, but I will still go back and check what is my acceleration centripetal. So like in this case, acceleration centripetal is 6.34 meters per second squared. you should have got about 3,500. I'm rounding hard, but. Ah. Now, 3,500 is a lot of force, but what is the weight of this car? 9,800. Now watch this. The other nice thing about this particular setup is this. Let's say I switched the conversation and I said, hey, boom, there's the car. What changes about this math if I ask you about the driver? Does the force diagram change? No, they're at the same speed. They got to go through the same radius for the most part. Maybe a small amount different there. Force gravity still has to be down. Force normal still has to be up. Okay. Does the math change to find the force normal on the person? No. What is the only thing that changes if we want to look at the person rather than the car? The mass. You plug in the mass differently. Why is this so big? Because we were talking about a freaking car, not about an actual person. What does this tell you? By the way, you should experience, if you look at this part, if I factor out the mass, you should experience an acceleration necessary of 6.34, or your normal acceleration, or your normal weight. Come on. They need to go. Is about 35% of what it normally is. So yeah, it's going to feel really weird when you go over that hill because you're not experiencing the same force upward that you normally would. So if you weigh like 100 pounds, you would feel 35 pounds pushing up on you as opposed to